Okay, so welcome back for the second lecture. It will be Hugo's first or second talk, depending on how you see it. Sorry for the slight delay. Okay, over to Hugo.
Thank you. So the last 4 lectures will be devoted to our joint result with Michael Eisenman on marginal triviality for the 4D Ising model. And today's lecture will mostly be a further explanation of the context, and we will finish at the end with a statement of the results. Tomorrow, I will develop the tools that we will use to prove the results. And in the last 2 lectures, I will provide you with a proof, but I mean a proof in a simplified context, meaning assuming something that is what should be happening, but which is not something we are currently able to prove. So the actual proof is technically more demanding because we don't have this assumption. Basically, we will assume that the spin-spin correlation behaves like the Green function in the 4D Ising model at criticality, which is definitely what happens, but we don't know how to prove it. But already there is some work to prove marginal triviality. But in some sense, the juice is already there. So I would restrict to this context. Okay, so today, so lecture 1. It's going to be the context and the statements of the result. Okay, so why do we want to prove what we are going to prove? Well, there are basically 2 research agendas that are connected to the result. The first one is something that I don't know so well, but which is constructive Euclidean field theory. So how do you construct random distributions in dimension 4 in particular? And why would you like to do that? The second research agenda will be more, closer to what I do for a living, which is statistical physics at criticality. Just can you describe the large-scale behavior of a critical system, and in particular the 4D Ising model? Let me start maybe with the motivation from constructive Euclidean field theory. So what's the goal there? There is a famous result by Osterwalder and Schrader that allows to translate, if you construct, it's kind of a recipe to go from quantum field theory in 3D, so in Minkowski, so 3D plus 1 time dimension. It explains how this quantum field theory, like a rigorous quantum field theory satisfying Weismann axioms, so some well-defined axioms, how you can connect this to a Euclidean field theory. We are probabilists, so Euclidean field theory just means a random distribution, okay? That will satisfy the Weismann's axiom, will translate into certain properties of this Euclidean field theory. Namely, let me mention them. They will need, for instance, that the correlation in your system, in your Euclidean field theory are analytic in each coordinates, for instance, things like that, that they have Euclidean symmetries, reflection positivity. I will come back to that much later, maybe on what I mean by that, and some permutation symmetry. So, there is a clear, I don't want to be discussing it. It's not the heart of the lectures, but there is a clear recipe to go from the quantum world to the Euclidean world, okay, in 4D. And typically, on the Euclidean world, so I will not discuss the quantum world, but on the Euclidean world, the question of constructing this Euclidean field theory is basically the question of constructing this type of object. So integrals that will look like 1 over normalization times integral of exponential of f of phi exponential. So for now, nothing is well defined. I will exactly discuss this in a minute. Product over x in Rd d phi x. So you want to make sense of quantities that will look like the integral of a certain functional of phi. Phi would be some kind of function, in fact, distribution, but something that will look like something like that. Function from Rd. Here it will be an infinite product of Lebesgue measures, for instance. And you would have an Hamiltonian h of phi, and h of phi would typically look like integral of gradient phi of x squared plus integral of p of phi of x dx. So here it's also dx, where p is typically a polynomial. More generally, here you usually want to be putting a quadratic form, but let me focus on this thing. So when you write things like that, you see already that there are many things that are not so well defined. The first one is that this infinite product of Lebesgue measures makes no sense. So here there is a difficulty in just making sense of this measure. And in general, when you will make sense of a measure like that, what you will end up with here is that phi will be a distribution. And if it is a distribution, then the gradient here becomes something ill-defined. Okay? And also just in general, there will be a problem also of just, so this is what we would call small scale divergences, like gradient of your distribution will make no sense. But you will also have large scale problem that maybe this thing here is not even finite, right? Because just phi is too big in average. So, you know, when you sum over everybody, you would have, over the whole space, you would have. So there are many, many problems when you define this type of objects. I mean, when you want to make sense of this type of objects, so you can ignore them, which would be maybe the physics way of doing. But here we will need to really make sense of these things rigorously. I should tell you what the type of functional you want to be looking at here. So f of phi typically, because we keep in mind that we may be forced to take phi as a distribution. So this functional will typically be the average of phi against a smooth function. So let's say compactly supported smooth function. So that's the goal. Can we make sense of quantities like that? Of course, then I mean, you have freedom in the choice of the p. And there are p's for which it's more or less trivial and p's for which it's more interesting, but harder. Let me just mention one other approach to this type of things is that just by linearity, when you look at, say, correlations between, so let's say you look at correlations between different observable t of phi. So let's say you take n smooth functions and you look at these correlations. Just by linearity, if you made sense of something like that, then the natural quantity, I mean the natural expression for this would be that it will be an nth integral, and you will have a f of x1, f of xn, times a certain function depending on x1, xn, dx1, dxn. And this function somehow should be interpreted as the correlation of phi of x1, phi of xn, even if when you look at the distribution, that doesn't really formally make sense. Okay, but you can think that in an ideal world, you would have an expression like that. And this Sn of x1, xn, it's called the Schwinger function. And usually physicists go around the difficulty of defining this type of object formally and the distribution phi formally by just saying that they are going to work with the Sn of x1, xn, which would be an analytic function in each coordinate, which will have the right symmetries, etc., etc. So that's usually the way of contourning the difficulty in a reasonable sense. I'm not actually blaming anybody here, is to simply work directly with the Schwinger function. It's a correlation, if you want, in your system. Okay, so we will see that actually most of what we are going to do is going to be dealing with the Schwinger functions, but it will have a clear interpretation in terms of the distribution phi directly. Yes, of course. So F, oh, yeah, you are right. Thank you very much. Thank you. Okay, so let me give you a first example. Which is kind of the archetypical example, which is assume that P of x is just quadratic. Okay, so here you put b phi of x squared. When you do that, you have something quadratic, so you immediately see that you get something Gaussian. Okay, so in this case, we will come back to this later, but what you expect to see, so this should lead to a Gaussian process. I will actually rediscuss this in more rigor a little bit later. So you get the Gaussian process, and in particular, what I wanted to say is that because you get something Gaussian, when you express S, when you want to look at the Schwinger functions, what you see in this context is that the Schwinger functions, they satisfy the Wick rule that I mentioned yesterday. So sum over every pairings of the product for I equal 1 to n of S2 of x by 2i minus y, x by 2i. Okay. So in this special case, there is a natural structure for Schwinger functions. I mean, a natural expression. You can always get back to the 2-point correlations. So that's, for example, one. I mean, this was just a parenthesis. And there will be another example that we will discuss, much more important example for us, which is if you take something quadratic, quartic, sorry, bx2 plus lambda x to the 4. By the way, here, in order to avoid having divergences, maybe you want to take the polynomial to be even, just to, right, we get exponential minus this integral. If p start to have odd powers, then it's going to be a little bit problematic. So the next level of difficulty is to add lambda x to the 4. Okay, and this is called the 5-4 model. I mean, Euclidean theory. And the big question, in some sense, is, for now, nothing is well defined. If you define things correctly, is actually 5-4 different from the Gaussian case? I mean, are examples 1 and 2 different. And it's not that obvious. Of course, formally, when you look at this like that, you think, okay, there is a lambda x to the 4, but because we didn't define things correctly, maybe when you actually define correctly, then the phi you will obtain is nothing more than, again, well, Gaussian free field, which will be what we get in example 1. So that's the question. And in fact, the answer depends on the dimension. Okay, so how do we go around the difficulties that I mentioned here? Well, usually what we do is that we introduce a cutoff, right? And there are different ways of doing it. You can introduce cutoff by doing what we call a Fourier cutoff, so going in Fourier space and cutting off the small values of P. You can introduce stochastic partial differential equations and try to work with those. So, and they approximate, and in large times, they end up with the process you want, the distribution you want as a stationary measure for the dynamics. Here we are going to take a more pedestrian approach. There is another way of doing the cutoff, which is just to like discretize in space. Okay, so you can discretize. So in order to solve divergences by introducing a cutoff. I'm going to call it a space cutoff, but I mean, I don't think that this is actually really a term that is used. So what I'm meaning here is that I'm going to work on a lattice. So I'm not in RD anymore. I'm on delta, or even I'm going to introduce lambda RA, which would be by definition minus RR to the D intersected with AZD. So I take a fine mesh size lattice and I do two cutoff. I mean, so the first cutoff is small scales, and this is A. The value of A is kind of telling me my cutoff. So the smaller the A, the smaller my the more relaxed my cutoff. And I also do a cutoff in large scales by reducing myself to a finite lattice, a finite portion of the lattice. Okay. And now when I look at this, I'm going to introduce what was before a function or a distribution on RD. Now here I'm going to consider it as a function on the vertices of my finite graph. So now phi is like that. So A and R, they have nicknames. So this is an ultraviolet cutoff. And this is an infrared. This has absolutely no like implication for the rest. I just mentioned it for the physicists in the room to try to make a connection to maybe what they are used to. Now let's define the equivalent. It is the equivalent of this thing. So I'm going to introduce h of phi, and this I already kind of mentioned it yesterday, as minus sum, or as sum of phi jxy, phi x minus phi y squared. Okay, and a priori here, x and y are in lambda RA. This is for this portion. It's a gradient portion. And for the other, for the second portion, well, I have two choices. I am always hesitating. Maybe let me put it like that. I'm going to add the natural discretization that I would have had there. Okay. And now when I look at this, notice that the thing makes perfect sense, right? It's a finite sum. And I can look at the model and even at the probability measure, but in particular, this type of observable. So if I look at phi and I integrate against a certain observable, there is a perfectly well-defined quantity, Z, that you will get by just doing here the nth integral. So here there is one integral per vertex in lambda Ra, and you get x of phi exponential of minus h of phi. And here it's a product for x in lambda Ra of d phi x, where this is just Lebesgue. So there is no problem of definition. Everything is well defined. And the question is, can I, in some sense, remove the cutoff? So what happens when R goes to infinity and A to 0? And of course, the answer will depend on P. So that's somehow the approach when you think of the Euclidean field theory approach, problem. And maybe, I realize that, yeah, maybe I can give you the example of example 1 to see a concrete realization of the program in a simple case. Okay, it's not going to be a full description of what happens, but at least maybe back to example 1 can be helping a little bit. Actually, maybe this is a little bit far. So maybe. Okay, so back to example 1. So for example, example 1, P of phi, P of x, I remind you, is like bx squared. So when you do that, you realize that you have another way of writing this thing in a very concrete fashion, which is that x of phi is just 1 over renormalization. Still our infinite product, there is x of phi. And here you can write exponential of minus sum for x neighboring y, for xy of jxy. Oh, by the way, sorry. Let me actually restrict maybe to jxy, which is nearest neighbor, meaning 1 if x is neighboring y and 0 otherwise. This is not a requirement for the whole strategy, but in this talk, it's perfectly fine to restrict to the nearest neighbor. So here, you get that, and then you get a product over x of exponential minus b phi x squared d phi x. I'm just changing a little bit. You see, I'm putting this part into the measure. Why? Because there you recognize exactly the discrete Gaussian free field, right? Here you have a Gaussian measure and you are integrating. So this is discrete Gaussian free field. In particular, when you look at discrete Gaussian free field, you have clear, you know, for instance, what are the correlation of this thing. So, actually, sorry, it's massive. Theory, it's a massive one. So you know what are the correlation of the discrete Gaussian free field. In particular, if you look at S2, maybe let me put RA like that to advertise that for now we are working on a finite graph of XY is going to be the massive green function on the graph. So in particular, if you let R go to infinity, you get the massive green function in full plane. Okay, so G infinity. For instance, here you see that letting R go to infinity creates no problem. It's very easy to get rid of the infrared cutoff. And then in order to get rid of the ultraviolet one has to be a little bit careful, because if you let A go to infinity, this thing is going to go to 0, right? You need, because simply the distance between the 2 points is getting bigger and bigger. So what you want to be doing, and that was the second thing I wanted to mention, and that's why I wanted to do this example, is that you want to be rescaling your quantity. So here, for instance, typically, you want to be rescaling by A to the 2 minus D, and then this thing, this thing would converge to the continuum. This is a massive green function in the continuum. In order to make sense of all of that, you should have D larger than 2, but since I'm kind of thinking D equal 4 anyway, this works well. So if you rescale properly the function, the phi, then you get that the Schwinger function converges to a function in the continuum. And by the way, this function in the continuum, you see that it satisfies the Euclidean symmetry, for instance, that I mentioned before. And of course, you could do it for the 2 endpoint correlation using actually this formula. You see that by properly renormalizing the 2 endpoint correlation, you end up with something fairly explicit. So that's the approach when you think of it in terms of Schwinger functions. You could also think of it in terms of distribution. So when you are in the discrete, you want to be defining the equivalent of, well, what is good is that it didn't erase so well, so we still have it here. The equivalent of this thing, right? So what would be the equivalent of this here? It would be A to the D integral or sum for x in lambda RA of f of x phi of x, right? This would be the equivalent of A to the D is here to make sense, to bridge the gap between sum and integral. So when you do it like that, you realize again that if you rescale the phi properly, then this thing is going to converge. So remember here, we were rescaling in such we were multiplying by A to the 2 minus D. So this for each phi was corresponding, right, to multiplying by A to the 2 minus D over 2. Okay. So here, if I want convergence, I should be multiplying by A to the 2 minus D over 2, because I have only one phi, right? So if you do this renormalization, which, here maybe I should, so this is like A to the D plus 2 over 2, then this TFLR, so TFRA, sorry, of phi is going to converge as a random object to something that I will be able to call T of f phi in the limit for phi, which is a random distribution. And this random distribution is a massive Gaussian free field. And in fact, you can see this as a definition of the massive Gaussian free field. The discrete massive Gaussian free field makes perfect sense. And this convergence is actually nothing very complicated. Notice the following: this quantity does converge when A tends to 0 to, in fact, a Gaussian random variable. And this is easy to see. Let me just exemplify it, like show to you how you do. Let's take the characteristic function of this. For instance, sorry, let's again take infinity here, because again, there is no problem with taking the limit. So let's look at this. Okay. So this is sum for n equals 0 to infinity of 1 over n factorial z to the n. In fact, it's easy to see that only the even things get non-zero. And here, so this quantity this is just sum for x1, x2n of fx1, fx2n, and there I get s2n, x1, x2n, where this is the Schwinger function for the discrete object. And using the Gaussian process here, using the V-close, sorry, when I rewrite here, there, I'm just going to get sum for pi pairings. And this thing is going to factorize super well. It's going to be just sum over xy of fx, fy, s2 xy. And the sum of the pairings, in fact, I mean, here, I mean, maybe it's x pi 2i minus 1 and x pi 2i. Sorry. And S2 of x pi 2i minus 1, x pi 2i. And the important thing is that this quantity now is just sum over xy of f of x, f of y, S2 of xy. There is no correlation between the different product of I. So this is always just sum over xy, fx, fy, S2 of xy. And this is just the second moment. So overall, I just get the number of pairing, let's call it P to n, times the second moment to the power n. So here, what do I get? When I replug here, I just get exponential of minus z squared over 2 times tf infinity a. I have problem with r and infinity, apparently. So I just get this like that, because that's what I would get for a Gaussian process, where I exactly have the same relation between the nth moment and the second moment, right? So as soon as I have this, then when n goes to infinity, when a tends to 0, so when a tends to 0, I exactly get that Tf infinity a of phi converges in low. Oh, sorry. I hope everybody had this. I struggled the first time. I'm not rewriting it. So in conclusion, EF infinity A of phi converges in law to a normal random variable with the variance, which is the limit when A tends to 0 of TF infinity A of phi squared. And this thing when I look at the expression, so it's the right sum. I mean, so this is going to converge to the double integral of f of x, f of y, and I will have here massive Wien function. Right? Because this thing converges to the right thing when properly renormalized. So overall, my point is that you can define, in fact, the massive Gaussian free field using the discrete process exactly like that. It tells you that there exists indeed that this object is. Okay, so that's for the simple example. The question is what will happen as soon as you have the quartic expression, and that things here become more complicated. But notice that one thing that we can keep in mind from example 1 is that in some sense there will be the question of understanding how maybe the 2-point correlation behaves. And then more importantly, in order to get expression like that, which will be what we will be seeking for, we will be seeking the limit of this quantity. Then what we need to know is somehow how you express the 2nth moment in terms of the second moment. So how you relate the 2n point correlation to 2-point correlation. And we will not be able to prove that you have an exact Wick law simply because it's wrong. But the goal will be to prove an asymptotic one. And this matches what I said yesterday. The statement of the theorem was actually giving an approximate Wick law. So we will be exactly looking for that. Okay, so let's move to the second approach. I mean, second, like perspective on the problem. Because up to now, notice that there is no Ising model involved, right? I never mentioned the Ising model. So the stats make perspective. There, maybe I'm going to go a little bit faster on the definitions because probably you already saw a bunch of those. So there is a measure that is defined by the following. So you are on a graph. There is a parameter beta. Here I'm going to write it like that, but maybe I'm not going to use the Ising too often. So there is a measure that is defined by the following. You renormalize, and then you put sum for sigma in plus minus 1 to the vertices of your graph, so G, that I identify with G, sorry, of f of sigma exponential of minus beta edge of sigma, where edge of sigma is minus sum for x and y of jxy sigma x sigma y. And here again, jxy, I'm going to fix it, but it's not mandatory, but I will do it in this talk, to be 1 if x is neighboring y in G, and 0 otherwise. So this is a classical definition of the Ising model. Now we have variable on each vertex, and they are taking value plus or minus 1. We saw several examples of that already. And in the previous talk, for instance, the jxy were random. Okay. So when I look at the Ising model, what I'm interested in is the behavior of the model as a function of beta. And in particular, there is this classical thing that you all heard about, that there is a critical parameter beta c. So you can, by the way, you can take G to be lambda RA if you want. In fact, the A will not play an essential role for now. And you can, or let's say lambda R. So when I say lambda R, I mean that A equal 1. Okay. So I'm looking at a finite piece of the d-dimensional lattice. And what you can do is you can let R go to infinity. Again, it's very easy. And you get a measure on ZD directly. Okay. And the goal in the Ising model is to understand what is this measure. Okay. And there is a dependency in beta. So there is a critical parameter. Above this critical parameter, the correlations, let's say sigma 0, sigma x, for the Ising measure on ZD, they converge when x goes to infinity to a quantity which is non-zero. While here, in this regime, they decay exponentially fast to 0. So there is a phase transition between an ordered phase and a disordered phase. Okay, so this phase transition happens at a critical parameter, beta c, and the goal of the statistical physics, statistical physicist is to understand what happens at beta c and how it goes from this disordered to ordered regime. And usually what you are interested in is the large-scale behavior of your system. So how does it behave, in particular, when you look at beta c? So the question would be at beta c, how does, for instance, sigma 0, sigma x, ZD beta c, Ising behave? So yesterday you saw that we proved that the phase transition is continuous. And basically this is actually saying, so continuous phase transition is saying this quantity goes to 0. When x goes to infinity. Okay. In fact, you can say a little bit more than that. Once you have that it tends to 0, there is this marvelous tools called infrared, called reflection positivity. So this, I will state it as a theorem. So the reflection positivity implies the following, well, let me call it directly infrared bound. The infrared band is saying the following. It's saying that when I look at sigma 0, sigma x, ZD beta, let me drop the Ising, right? And actually the ZD as well. So let me, for now, I will just drop ZD and drop Ising, both for your race and mine. So this quantity minus m star of beta squared. Okay, so if I look at the spin-spin correlation and I subtract the magnetization squared, this is smaller or equal to 2 over beta times the green function. And this is really the discrete green function. The green function, the random walk. So not in the continuum, really the discrete. It's not a trivial theorem. once you observe reflection positivity, it's actually not difficult to get. And it's a marvelous tool because, in particular, notice that once you have proved continuity, then if you are at beta C, you know that this is 0. So it gives you actually a very good quantitative bound on the spin-spin correlations. They are smaller than the green function. So they decay as 1 over distance to the d minus 2. So in particular, for beta equal beta C and d larger than 2, you have then sigma 0, sigma x, beta C. It's smaller than constant over x to the d minus 2. I'm cheating a little bit here. It's only something in Fourier. Normally, if you want the side to side here, you should get a constant, in fact. Not, so disregard a little bit this exact value, sorry, and keep just that in mind. Okay? It's true for any beta. Yes, yes, yes. And it's true for any beta with a constant here. The 2 over beta is if you transform this in Fourier, because here you have a space estimate. If you take the Fourier transform of this is bounded by 2 over beta times the Fourier transform of the vector. But if you go to space, you need to work a little bit. Of course, I mean, the Fourier estimate is just an average estimate. So you need, in order to translate it into a pointwise estimate, you need to work a little bit, and you lose the exact constant, or at least you get a constant which is not sufficiently nice to be remembered. Okay, so you get the 2-point function, and what happens is that, in fact, and this is going to be our assumption under which we are going to work in the next lectures, even though it's not necessary, I should say, to get the result. So in fact, conjecture for d larger or equal to 4, sigma 0, sigma x, beta c is of the order of the green function. So it's not just that you have an upper bound, it's actually also a lower bound. Okay? And this can be obtained it's not too difficult to get that in very high dimension. I mean, sorry, in very high dimension, less expansion allows you to prove that. We found with a PhD student, we found a very cool way of getting it for any dimension larger than 4 strictly. In dimension 4, we are still we still don't know how to prove it. And because I'm going to work in dimension 4, I'm going to keep this as a conjecture. Yes. Oh, it is. It's not obvious. It follows from a correlation inequality. The spin-spin correlations here. So in fact, this quantity or this one are the same. You will get the same limit. You can take the plus boundary condition here. Why am I saying that? Because if I look at this plus boundary condition here, I can use Griffith's inequality. It's positively correlated. So the correlation of the product is larger than the product of correlation. And then this quantity is just a magnetization, and this one is the magnetization. That's how you would do it. So it's not entirely obvious. You are entirely right. Okay. Where am I? Yeah. And something which is much less obvious and which is the next step when you try to understand the critical system is what happens when you look at more than 2 points. Okay? So question, what happens when you look at more than 2 points? So what happens for the correlations between, say, 2 endpoints? And typically what you would like to do is you kind of expect then here that means that it decays like 1 over distance. Oh, sorry, there is no y here. 1 over distance to the d minus 2. So here what you would like to be doing is that if you look at points that are roughly at distance capital level of each other. You want to rescale by the right thing and take the limit. Okay? And now you recover exactly what we were getting before. So let me be more precise. So for instance, what would be the limit? Ooh, okay, yes, I'm nearly done. So if you rescale by this quantity, does it have a limit? So let's say you fix the point xi, you take the point lxi, so they are further and further away. You rescale by what you expect. For 2 points, you should rescale by 1 over L to the d minus 2. So for 2n points, you should rescale by this quantity, the power 2n, sorry. What is the limit? And you recognize that this is roughly the same question, right? Exactly the same question as what we did for this model that we defined on lambda Ra, right? With the phi x to the power. It's the same question for Ising. So let me just take 1 minute. I know that I'm over time. Oh, it's blinking red. This thing doesn't move, right? It's not, cannot get to me. Let me just in the last minute, tell you what's the connection. So we end up with the same question for 2 different models. What is the limit of 2 endpoint correlations when properly rescaled? So the link is kind of the following. So remember here we are taking, so for Ising, we are taking sigma in plus minus 1 to the n. We defined what we call a lattice phi4 model. And the lattice phi4 model, if you remember, phi was a function from the vertices into R, right? And here the Hamiltonian was doing something like it was, so let me just write it here. So Hamiltonian was sum of phi x minus phi y squared plus sum of p of phi x. Okay? Here you can actually see it as minus 2 phi x phi y, right? And put just the phi x squared in this quantity, just changing the p. So we were looking at quantity of this type. And in particular, remember example 1 was p equal b phi x squared. And it was giving the discrete Gaussian free field. So if you take b phi x squared, you get a Gaussian process. But I told you there is example 2 where you put lambda phi x to the 4. And actually, you could also put a constant here. This was example 2. So now observe the following. Here, if you take lambda, which is minus b over 2, here you get something like lambda phi x squared minus 1 squared, if you take the right c. And of course, I mean, putting a constant c doesn't change anything to your measure. So if lambda equals 0, you get Gaussian free field. Lambda intermediary, you get something that looks like phi4. But lambda going to infinity, what do you get? You want this to be 0. You get exactly the Ising model. So in fact, the phi4 model is an interpolation in terms of having stronger and stronger correlation. It's an interpolation between Ising on one side and the discrete Gaussian free field on the other side. Okay? So why will I work on the Ising model? Because in some sense, that's what is the farthest away from a discrete Gaussian free field, from a Gaussian process. And actually, I will prove that in dimension 4, if you start from the Ising model, you get something in the limits, which is Gaussian. So in fact, you will have to trust me, but everything in between can be also proved to go to this. So the phi4 interpretation from the first perspective is similar to the Ising interpretation that we got in the stat-make perspective. And this Ising is the worst that can happen in terms of correlation. It's the furthest away in this class of models for quartic interaction. It's the farthest away from Gaussian a priori. Sorry, I took 3 minutes too much, but I wanted to end up on this point. So tomorrow we state the result and we start developing the tools that we will use. Thank you very much for your attention. Any question? Yeah.
Some questions? Yeah.
Can you comment why d equal 4 was important here? I mean, I don't
Why?
see why d equal 4 is important, 4 dimensions.
Okay, so d equal 4 is not important. D larger or equal to 4 is important. For d larger or equal to 4, you will get this behavior and you will get, in fact, Gaussianity. Okay, so you will have that the two endpoint correlation have an approximate vector. It was proved in dimension 5 and more. But dimension 4 is a dimension which is relevant from the point of view of the first perspective, the Euclidean field theory perspective. And it's also the hardest one. So that's why it took more time. And that's why I'm going to present this one, is because that's the hardest one. And you will see very easily why. At an interpretation level, I will explain to you why dimension 4 is harder than higher dimensions. In dimensions 3 and 2, it's just wrong. This limit is wrong. So in this thing, you should have a plus eta here, and this eta is non-zero. So the exponent is not d minus 2. Okay. In dimension 2, for instance, it's 1/4. That's the first thing. And then anyway, even if, no, I mean, it's not necessary to have this green function estimate to get Gaussianity. You could imagine that the 2-point function behaves differently. It's just the Gaussianity is really how you relate the two endpoint correlation to the 2-point correlation. This could be true even without having the green function estimate for this. But it happens that, in fact, the two things are intimately related. So if you don't have that, you don't expect to have Gaussianity. So in 2D, it's proved you don't have a Gaussian process in the limit. You have a 5-4-2 distribution, and it's not Gaussian. And in dimension 3, it should not be Gaussian either. It's not known. We don't know how to prove that the 3D Ising model, for instance, is non-Gaussian. Yes, yes. No, you could take first A to 0, then R to infinity. You can take them as you want. It will not change anything. No, not change anything. It's much more practical to do R first, but there is no problem in doing. In this type of cases, you don't have. I mean, you control very well what happens at infinity. It's not the same thing as in SPDE community, for instance, where sometimes it's very difficult to actually get to infinite volume. Here, it's not a problem. In some sense, the problem is a little bit solved by the continuity of the phase transition. It's a little bit saying like the large scale behavior, you understand how it behaves.
We'll move to the next talk.
Thank you very much.